Today we are going to start a new unit about thermodynamics. Thermodynamics is the study of relationship between the energy and the work associated with chemical and physical processes, and it provides some tools to predict if a reaction will happen or not. We have already talked about thermochemistry, and we have described heat and how heat flows during chemical reactions and phase transitions. Now we are going to introduce the concept of spontaneity of reaction, and we'll introduce some additional function of state, and in particular entropy and free energy. So I think you would all agree that what is presented in this slide is not going to be a spontaneous process. We all know that rock wouldn't go spontaneously from the bottom of the hill up to the peak. The only way a rock could move in that direction if someone is going to push it, so it requires some intervention from the outside. The spontaneous movement of the rock without any external intervention would be in the opposite way, going downhill. So we need to come up with a definition of spontaneous process versus non-spontaneous process before we can worry about how to predict that. So we could define a spontaneous process as something that occurs without outside intervention, as opposed to a non-spontaneous process in which there is the need for this intervention from the outside to trigger, to make the thing happen. So let's see some examples. If we know that objects on the top of a shelf may fall, right, spontaneously. So from a position of high potential energy, they would go spontaneously down where the potential energy is lower. So a first observation is that in spontaneous, in this set of spontaneous events, let's say the driving force is a decrease in potential energy. We may still object that. For example, if we have a cup, like it's showing in this drawing, right? For the cup to go down and break, there has to be, sure, it's spontaneous, and meaning it happens without intervention, but there has to be a minimal intervention, like the cat should kind of push the cup over the edge, right? So what if after that, then the rest of the fall process would be spontaneous. Let's see another example. Here you have the familiar cycle of carbon, right? So through photosynthesis and the energy that's coming from the sun, the CO2 can be transformed into different organic products, basically sugar, and from sugar cellulose and starch and so forth. So that's building up the mass of plants and trees. And so this process is endothermic because the energy of the sun is coming into the process. And then you have on the other side combustion or respiration. So we can either burn the branches of the tree, or we could eat the seeds and the plants. But in all instances, the reaction can be simplified as sugar being transformed back into carbon dioxide. So that part is giving off energy and is exothermic, and it can be regarded as spontaneous. So we might agree that photosynthesis is the non-spontaneous side and combustion is the spontaneous side, and basically they are two sides of the same coin. Now some of you may object to considering burning spontaneous because, as you know, to start a fire you need to provide, it starts with a match, and so if you have a pile of wood and you're trying to burn it and you don't have a way to ignite to provide that initial trigger, the burning is not happening. So if we would be in class and we would be having a discussion about this, I'm sure some of you would object to considering burning spontaneous, because if spontaneous means it happens without intervention, there is initially an intervention. Now when we did kinetics, right, at the beginning of the semester, we got familiar with the concept of activation energy. So that's what that initial flame is doing to the fire. That is a bit the same as in the example before, the cat pushing the cup over the edge. So there is an initial intervention, but after that I do not have to keep providing energy. Instead, in photosynthesis, for the photosynthesis to happen, there has to be this provision of energy constantly. So we could be more specific about our definition of spontaneity and say, well, a process is spontaneous if, after being initially triggered, it will continue without the intervention of energy. And I guess at this point we would all agree that combustion would fit in this definition. So there seems also to be a pattern in which, when I consider the direct reaction, let's say photosynthesis, and the reverse reaction, respiration, so this is just the same reaction flipped, if one is spontaneous, the other one is not spontaneous. So we might have noticed a pattern at this point, putting together those two examples, where in both instances the spontaneous part, the spontaneous phenomenon, consisted into going from high energy to low energy, because if a reaction is exothermic, right, we have learned by looking at the energy diagram that an exothermic reaction, as the level of energy of the reactants is higher than the level of energy of the products. And that means that there is let's say, some energy missing by the end of the reaction. This energy is the energy released into the environment. And this is what makes the reaction exothermic, as opposed to an endothermic reaction, in which we need to provide that energy because the products will end up having more energy than the reactants. So this exothermic would be combustion or respiration, while this endothermic would be photosynthesis. So we might, at this point, be reasonably convinced that we have figured out how to predict if a reaction is spontaneous or not, and the spontaneous reactions are exothermic in the sense they share the fact that the system initially has more energy and after the reaction has less energy, and this release of energy in the surrounding is what drives the spontaneity of the reaction. However, I could provide you examples that would kind of disprove your theory, because you all know that if we have if we throw in the air a bunch of coins, and if the number is sufficiently high, we may have, typically, let's say, the more likely scenario is that we end up with half of them facing up and half of them facing down, and it's extremely unlikely that they all, 100 coins thrown randomly, they will all land on the floor, all heads up. So this means this is an example of a spontaneous process, the way the coin will distribute, that has nothing to do with the energy. Another example is, so let's see this example. We have the expansion of a gas, right? So we have two containers. One has a certain amount of gas, so there's going to be a certain pressure. Let's call it P. In this container, we have the vacuum that's letting wall for empty, so that means that the pressure here is 0. Now the two containers are separated, and they are in a system that is isolated. So this thick double line wall means that the whole system here is isolated. There is no exchange of matter of energy through the border of the system. So let's imagine we open the communication. Now the molecules of gas are free to move back and forth. So what's going to happen is that some of the molecule will move in this direction and some of the molecule will move in this direction, but eventually we will reach a steady state, but the number of molecules in the two containers is the same, and therefore the pressure is the same. So the pressure will kind of equalize. So the spontaneous direction of this transfer of molecule is always to going from a situation where they are all on the same side to a situation where they are equally distributed. If we would start from this distribution and we would open, we would never get that. And also you need to remember that to simplify here, we have probably 20-25 molecules. I didn't count them, but for a real gas, the number of molecules it's an immensely large number. So that it further decreases the chances that they all end up on the same side. So what's the energy? So our theory so far is that there's something to do with energy. So this spontaneous process is the one that goes from high energy to low energy. But is there energy involved here? So we know that the change in internal energy can be calculated by the sum of the heat exchange and the work exchange. And the work can be calculated as the product between the pressure times the change in volume. So in this case would be an expansion. So the first thing that we're going to consider is that the work, it's a work of an expansion against the vacuum. So it's like trying to open a door and the door is open, there is no resistance, right? So whatever is the change in volume, and in fact we don't have the deformation at all, if P is equal to 0, it doesn't really matter, whatever is the value of delta V, 0 times whatever gives you 0. So the work is going to be 0. On the other hand, we know that the system is isolated, right? That was the scenario we have thought about initially. So if the system is isolated, delta U is going to be 0. So because delta U is equal to Q plus W, and we know that delta U is 0, we know that W is 0, the only possible value for Q is also 0. So there is no energy whatsoever involved, not in the form of heat, not in the form of work. So energy cannot be the answer. The relative value of the energy cannot be the answer to our quest for the determination of spontaneity. Finally, it's not true, although the vast majority of spontaneous reactions are exothermic, there are in fact some reactions that are endothermic and are still spontaneous. And I could tell you, for example, melting of ice at room temperature is endothermic and is spontaneous. Most acid-base reactions are exothermic, like if you mix sodium hydroxide and hydrochloric acid, but the reaction between vinegar and baking soda is endothermic and is spontaneous. It's the one that you did several times in the lab with a lot of foam, and it's the one that you used to do the volcano simulation in, science fair in middle school and so forth. Another one is the dissolution of ammonium nitrate in water that's used in instant cold packs, spontaneous and yet endothermic. So there are a few reactions that are endothermic. So, but there is still the fact that a lot of reactions that are exothermic are spontaneous. So maybe being exothermic helps, but it's not all that there is about it. There has to be something else that we still don't know. So we can say that the direction of a spontaneous process is not governed solely by the energy change. That is a factor, but is not able to explain everything. So we're probably missing something in the picture. So let's go back to our first law of thermodynamics. And the problem with the first law is that it doesn't really give us any limitation into the transformation of heat into work and vice versa, right? Because pretty much it looks like we could transform a certain amount of heat into work and vice versa without any particular problem. So that's where the necessity of a second law of thermodynamics comes into place. So let's go back to our example of the gas expanding into vacuum. So what's happening here is that, and this explains also the coin example, what is spontaneous? It's a process that increases the disorder of the system. This is a very ordered system. Everything is on the same side. After the spontaneous transformation, we have more spread. The molecules are more spread. Same with the coins. I think the coins all turn the same way. Would be a very would be a very ordered set of conditions, as opposed to having half of them facing up and half of them facing down. That's more a random, let's say, disorder array. We can look at with the same mind setting to another process that we know being spontaneous. That is that when we put something hot in contact with something cold, the heat transfers spontaneously from the hot body to the cold body and never the other way around. And so if we consider the fact that heat is a form of kinetic energy, so if we have the two bodies at different temperatures, is like order in the sense that the heat is all on the same side. The kinetic energy is confined on the same side. When we put them in touch, the kinetic energy tend to distribute in order to have larger spread of its values, and therefore we have more disorder. So spontaneous processes are processes in which there is a less uniform distribution of matter and energy. So we want to kind of consider the thermodynamic in the historical context in which it developed. The historical development of thermodynamics is tied to the Industrial Revolution that took place in England during the late 1700s and early 1800s, and machines were by definition the focal point during the Industrial Revolution. And one of the central preoccupations of the industrialists and consequently of the scientists that were working to help the development of the factories was the efficiency of those machines, and efficiency in terms of ratio between output and input. The more output that could be produced with a given input, so eta would be the efficiency of the machine. The more output that could be taken out, provided a certain amount of coal, was resulting in a greater economic advantage for the owner of the factory and supposedly for the society as a whole. So in the history of science, the mechanical equivalent of heat states that motion and heat are mutually interchangeable, and that in every case, a given amount of work would generate the same amount of heat. So it's sort of a constant relationship, provided that the work done is totally converted into heat energy. The mechanical equivalent of heat was a concept that had a very important part in the development and in the acceptance that of the principle of conservation of energy, and therefore it's establishing the foundation of thermodynamics. So at that time, scientists still believed the possibility of a perpetual motion machine, so a device that, you know, upon receiving an initial input of energy, because if you assume that a machine could work without even that initial input of energy, that would be in defiance of the first law of thermodynamics. But you could think, okay, I need to get the machine started and then it would go on and on forever. That would be, they still thought that was possible, right? And as it emerged that that work could be converted in heat, it began to seem possible that it could be converted directly back into work, thus making it possible to, you know, operate a perfectly reversible perpetual motion machine. Unfortunately, the law of thermodynamics dashed all those dreams, and the picture on the right shows you an aeolipile or aeolipile that is known as an Hero engine. It's a sort of a steam machine where the heat is making water to boil, and that's going to determine the movement of a heavy object that can be lifted, thus producing work. And it's really impressive to see how old this kind of design was, because it's 50 AD, so that's 50 years after you know, the birth of Jesus. So that took place in Egypt, that at the time was under the Roman Empire. The introduction of the steam engine was going to be one of the key factors for the onset of the Industrial Revolution. For the first time in history, there was a device that made possible to use it to produce mechanical work. In the next years, there were many efforts made to improve the efficiency of these machines, and eventually in 1824, young French engineer, his name was Sadi Carnot, he wrote a paper on the efficiencies of steam engines. And in this paper, he identified that for any engine to be able to convert heat into mechanical work, it was necessary to have a constant temperature differential. So he was only 28. He was a French military engineer, and he published these results about the efficiency of steam heat engines, and you can see a picture of him on the left side of the slide. And then later, Rudolf Clausius, who was a German physicist and much more serious looking, and you see him on the right side of the picture, he introduced a new thermodynamic property, a new thermodynamic state function, entropy. Entropy is related to the spontaneous heat flow. And this new property was expressed as the ratio between the reversible heat exchange and the temperature in Kelvin. And I don't know, but I see a pattern here between names, and you know, you're free to draw your own conclusions. So Carnot understood that cold bodies never export their coldness, so it's not cold going from something warm to something colder. It's actually a hot body to transfer heat to colder bodies until the two, bodies will have the same temperature. So as I said, entropy was defined as the ratio between reversible heat and temperature. So it's a function of state, and it gives it away because we use the capital letter S. And it's not really clear why the S was chosen. Almost, they were kind of running out of letters, basically. It's the spontaneous heat flow that accompany to a process and the temperature at which this transfer takes place. So Q is, as usual, the heat. Rev means reversible. Basically, it means a very, very slow, an extremely slow process that can be flipped, that can be reversed at any moment. And T is the temperature in Kelvin. So it's a function of state, but it has unusual units, because so far all function of state, like delta U and delta H, they were measuring joules. This is measuring joules divided Kelvin. So the units are its energy divided the temperature. So what do we mean by reversible process? What does this rev subscript means? It's an ideal concept. Is an abstraction. There is no real process on Earth that can be truly reversible. It's a process that can be run in the opposite direction at any time. So and this implies the process to happen at a very, very slow rate, so the system can be returned to its original state. And this, of course, it's a purely abstraction. So now it's time to watch a video. So again, I suggest you follow this link, copy and paste, or just click on it, watch the video, and then come back for the next slide. So in the movie, you've been introduced to the concept of microstates. So let's try to understand what we mean with microstates. A microstate, and that's indicated with the capital W, it's a specific configuration of the system. So it's like we have a system, like a test tube with chemicals in it, and we are able to take a picture of it and see how things are organized inside of it. Now, typically, in a system we have so many molecules, we have an incredible high number of molecules. But to understand a concept, let's start with something really simple. So let's imagine we have only 4 objects, right? So we have those 4 balls, and one is red, one is blue, one is yellow, and one is green. So we can tell them apart. So imagine we have 2 containers, and we are trying to figure out all the possible ways in which those 4 objects can be organized in those 2 containers, right? So the first possibility is to put all 4 objects in one of the 2 containers, the one on the left. And there is only one way to do that. So we have only one microstate for that particular configuration. Of course, we could put them, instead of putting all 4 of them in the left container, we could put all 4 of them in the right container. So, but again, there's only one way to do that. Now, if we want to put 3 balls in one container and the remaining one in the other container, that's kind of offering us more possibilities, because the one that's alone on the in the right container could be either the red, right? So let me get the laser. So it could be the red, or it could be the green, or it could be the blue, or it could be the yellow. So there are 4 different ways to arrange things so that 3 objects are on the left and 1 object is on the right. So let's imagine now we still have sort of the same arrangement, but the 3 objects are on the right container. So again, the one that's alone on the left can be the red, or the green, or the blue, or the yellow. So there are 4 different ways to do that. So in total, the different ways we can put 3 objects on one side and 1 object on the other side is 8. What about if we want to put 2 objects on one side and 1 object on the other side? Now there are 1, 2, 3, 4, 5, 6 different ways to do that. So if we are counting the probabilities to have those configurations, right? So the probability to have configuration A, all 4 objects on the left container, is only 1 out of 16, 16 being the total. If I count them all, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So I have basically 16 different ways to arrange things, of which only 1/16 is all 4 objects on the left. 1/16 is all 4 objects on the right. So basically, the one that has the largest probability is C. That is 2 objects on the left, 2 objects on the right. That has 6 out of 16 probability. So that's the more likely to happen. Okay, so that's the more probable microstate. And that's the one that implies the larger spread of objects between the 2 containers. So it's a bit like the thought experiment where we have the gas on one side expanding in the vacuum that we saw before. So Boltzmann was a German scientist, find out this relationship that connects entropy to the number of microstates. So W is the number of microstates. So if I take the logarithm of that, there is a proportionality between entropy and the number of microstates. So this configuration, where I have so many microstates, is the one that has the largest entropy. This has a little bit less, and this is the one that has the lower amount. K is a constant. It's called the Boltzmann constant. It's a very, very small number. So that means that for a small number of microstates, as I have here, S is going to be an extremely small number. But again, in chemistry, in a system, you have like, Avogadro numbers of molecules. So the number of microstates is extremely high. That means that the number you put in here, when you substitute into W, the number you put in here is going to be extremely large. So then even if K is a small number, S is going to be quite big. So let's say we are interested in determining the change in entropy during a chemical transformation. So it's as usual, the change in entropy is going to be final minus initial, right? So if the number of microstates after the chemical reaction is going to be higher than the number of microstates before, so is W2 is going to be larger than W1, then when you calculate delta S, you're going to end up with this formula. So if this is a larger number than W1, the ratio is going to be larger than 1, the logarithm is going to be positive, so the delta S is going to be positive. So if the reaction is such that the number of microstates is increasing, the delta S is going to be positive. If instead the reaction is such that the number of microstates is going to go down, then W2 is going to be a smaller number than W1. So the ratio is going to be negative. The ratio is going to be less than 1. That means that the logarithm is going to be negative. That means that delta S is going to be negative. So for any process in which W is larger than W1, there will be a positive change in delta S. And that's what's going to drive this, the